All right, so this video, we're doing piecewise functions, calculating, and graphing. So I have 3 examples here that I'm going to go through. The goal for each of these is to graph, but as part of that, we're also going to calculate. So I'm going to go through each of these. I'm going to try the best that I can to sort of make a nice color coordination bit here. So for f of x, this first one, part A, so part A, let's see what it's telling us. So f of x is the piecewise function, right? That's what the open brace is telling me. And it's saying that I have this function, this nice quadratic function, is what it looks like on this segment here, -3 to 1, including -3, not including 1, right? And then at 1, and including 1, it's going to be sort of glued together as the square root of x minus 1, okay? So let's first of all draw our little graph piece here. This is our hopefully end result look, right? And it's worth also noting or making a mark on here at the sort of important values. So I can tell I'm going to be stopping at -3. So if I did something like 1, 2, 3, -3, I'm also going to be stopping at 1, or I shouldn't say stopping, but I'm going to be transitioning at 1. And it's going to keep going on forever to the right. And in fact, I'll even do this. So it'll keep going like that. And I guess I should make this blue as well. Eee, that was foolhardy. Hubris, I say. So make this. So that's 1, 3, 5. Okay. All right. So what this says then is I'm going to have x squared plus 1. So what does that look like? Well, that's an x squared, which is our normal parabola shape, right? Normal u. But then it's shifted up 1. So it's going to be starting at this 0, 1 here. It's going to go up and left over to -3. So that's going to go up to, I guess I should have made this taller, but it'll go up here to 10 looking. So it'll have a spot over here. It's going to include that spot, right? So let me maybe be very careful when I'm doing this. So I want to know where it's at -3. So if I'm going to look at, this is the calculating part, if I'm going to look at f of -3, what is that? So what I do when I calculate this is I say, okay, -3. Which domain is -3 in? Well, is -3 greater than or equal to 1? Not so much. Is -3 between -3 including and 1? Yes. So it's on this row, which tells me then that I'm going to be using this function. So it's going to be -3 squared plus 1. Okay? I don't even need to care what this function is. It never shows up, right? I can just sort of erase that and not care about it at the moment because -3 is not in the domain, so this doesn't matter, right? This then, I can calculate. -3 squared is 9, 9 plus 1 is 10. So at -3, I'm going to get 10. Okay? Likewise, I'm going to check the endpoint. Now, I'm going to be careful when I write this. So I'm going to say, okay, what is f of 1? Well, f of 1, I would say, okay, is f of 1 between -3 and 1? Well, I'm not including 1, so it's not that. It is, however, greater than or equal to 1, so it would be this piece, right? So I would actually get square root of 1 minus 1, because now it's in this domain, so that piece I don't care about, right? So it's only this piece that I care about. This would be 0. So at 1, I get 0, and it's a closed circle, right? But if I get sort of infinitely close to 1, but I'm to the left, so as I'm coming over this way, I'm going to be on this function. So if I'm at like 0.99999, that's less than 1, I would be here. And the easiest way to do that is to use 1, but remember that I'm not actually including 1. So I would plug in, sort of as a cheat, I'm plugging in 1 to get 1 squared plus 1 is 2, which tells me that as I come around, I'm going to get really close to 2, but not including it. So I'm going to have an open circle here. Okay. Likewise, if I'm looking at the square root, right, this function is the square root of x shifted to the right by 1, so it's going to go off this way, right? So it'll go through the point 2 comma 1, and then it's going to go through what, 5 comma, so if we plug in 5, that'll be 4, square root of 4 is 2, so it'll go through this point. So it's going to look like this, okay? And when I'm done graphing this, I can actually now see, right, that this is the square root of x minus 1. And this is indeed the x squared plus 1. And I have glued them together, quote unquote, meaning that I went through one, then I stopped, and then I transitioned to the other. Note that they don't actually have to glue together literally, right? I have a gap here. This is what we would call, if you remember, the jump discontinuity, right? So it is certainly possible to have discontinuous results, which is what we can see here, okay? It doesn't always have to be discontinuous. That's sort of the excitement of the piecewise functions, is we don't actually know what's happening at these transition points, okay? So let's do another one and see how it goes. So let's say B. So I'm just gonna sort of divide this one off. So let's look at B. So this one I'm doing log base 2, right? So I'm doing this thing. So I'm doing g of x. I have this to the left of 0, this to the right of 0. So I'm just gonna, again, make a little xy plane here. So starting out, I want to know, okay, what is, let's do this. So I don't have any like leftmost point to check, which is what I did first. I don't have any rightmost point to check either. What I really have is the transition point. So I'm going to evaluate the g of 0. Again, technically g of 0 is wherever 0 is actually included, which is here, right? So that is going to give me log base 2 of 1 minus 0, because again, since 0 is in this row, I can ignore this entirely, right? I only ever calculate the one row where it's actually in the domain. And this is going to be log base 2 of 1, which log of 1 is 0. So at 0, I have a y value of 0. That's included. So I have a function, or I have a point here at 0. Okay. Now, if I go to the left of 0, I'm still on this log function. And log function is really, if you look at this, right, I have it moved to the left 1, because I have negative x plus 1 is really the way of looking at this. And remember, everything about x is backwards. So it does the plus 1 first, which moves it left 1, and then I flip it, meaning that instead of going sort of way down and over, it's going to go that way, but only from here. So it's actually going to go like this. And this is the log base 2 of 1 minus x. And if you aren't sure, you can plug in some values, right? So if I did, for example, so this was at 0. If I did it at, let's say, negative 1, then I would have 1 minus minus 1. So I'd have log base 2 of 2, which would be 1. So at 1, I should get 1, right? At 3, I would have log base 2 of 4, which would give me 2. So it would go up a little more, etc. So if you want to graph this carefully by plugging in specific points, go ahead. This is the shape that you should get, okay? And again, drawing attention to the fact that I filled in the circle at the origin because that was actually included here. Now in contrast, I can look at the other piece, which if I'm close to 0 but bigger, it's going to be this part. So again, I'm going to cheat a little by plugging in 0, but using an open circle because it's not actually, 0 is not actually on the domain here, right? So if I did plug in 0 here, I'd have 2 to the 0 plus 1 minus 2, which is 2 to the 1, 2 minus 2 is also 0. So as I go to the right, I have an open circle. So I have an open, it's getting kind of messy. blue circle, right, an open circle for the bottom piece. And then to the right, this is 2 to the x, an exponential, shifted left 1, but then down 2, meaning it's not flipped in either direction, so it's going to look like an exponential from here. So it's going to go over and up. And again, if I wanted to check, I could do something like g of, let's say, 1, which is now honestly in this blue section, right? Because 1 is bigger than 0, so I'm only looking at this piece. So I'd have 2 to the 1 plus 1 minus 2, which is 2 squared. 4 minus 2 is 2. So at 1, again, if I could draw worth anything, I would see that this point really should be, I guess, up here. So it really goes up even faster than I drew. So let's just pretend that 1 is way over here, and I have a terrible scaling, because this is really going to be the point 1 comma 2 if I could draw it all, right? As opposed to over on the other side where it's 1 comma 1. So sorry if it looks terrible. Oops, negative 1. It looks terrible because I did not plan that out well, but this is the idea, right? So you can graph a couple points and go over. Again, I want to point out that what I'm doing is, if I have endpoints, I'm plugging in the endpoints, but I'm being very careful when I do things where it's not equal, because if it's not equal, I need an open circle, whereas if it is equal, I can use the closed circle, right? So I plug them both in, but I'm cheating when I do the strictly less than, when it's not equal, because it doesn't actually exist there. Likewise, if I want to evaluate this function, like if I wanted f of 7, that involves just finding which domain, right, 7 would be in. 7 is not between -3 and 1. 7 is bigger than 1, so I plug 7 into just this piece and evaluate. So I get the square root of 6, okay? So I'm going to do some editing magic to get rid of this and move to C, where C is now a harder one because now I have 3 pieces. Oh, and sorry, I'll just point this out, even though it's sort of implicit here. So I have log base 2 of 1 minus x. This is now the function 2 to the what was it, x plus 1 minus 2. And so again, I have this piece glued to that piece, right? I have the log base 2 piece glued to the 2 to the x plus 1 minus 2 piece, and they're meeting at the x value of 0, which, as it happens here, also has a y value of 0. Okay? So, editing magic, abracadabra. And we're back. All right, so part C. So here I'm going to do, yet again, the same idea. So I have h of x. This one's going to be a little bigger, so I'm going to make the graph a little bigger. In fact, let me do the graph over here. And I'll do the calculations to the left. Sorry if that squeaked. So for this piece, I have something to the left of -1. This one's tricky, so I'm actually going to save this one for a little bit later. I'll do the other ones first. So here I have x squared plus x for -1 to 1. So again, I'm going to, just to point out, in case you're wondering, I can do these in any order because they are entirely different segments, right? That's the whole thing about Piecewise, is sort of this thing is unrelated to that thing. I'm just taking 2 things and mashing them together, right? So I can graph these in any order I want. I'm going to save this one to last because there's some trickiness just in terms of the algebra to do here. So here, I'm going to do this piece first. So x squared plus x, -1 to 1. So like all the other ones, I'm going to say, okay, this is a parabola. I know what shape a parabola is. It's a positive leading coefficient, so it's going to be facing up like a U. And it goes from -1 to 1. So I'm going to plug in those values to see what they are, so I see where the edges of the parabola are, right? So here, if I plug in -1, I'm going to get, so again, do this sort of very carefully to show. If I actually looked at h of -1, this honestly is, right, because -1 is in, it's hard to do this and be visible. It's actually in the domain for this middle piece, right? So it actually honestly is -1 squared plus -1, which this is +1 plus -1, so this is 0. So I'm going to have the point -1 comma 0 over here. So let me mark these things part way through. So I have one at -1, 0 here. Likewise, 1 is not in the domain of h of x here, and in fact it's also not in the domain here. So I've actually missed 1 entirely, and that's okay. There's no reason why any given point has to be in a domain for a piecewise function. But I'm still going to use the same cheating trick where I'm going to plug in 1 here, but keep in mind that it needs to be an open circle and not just, you know, a line and a closed circle or just a line, right? Because I need to emphasize that it's not actually in that value. So if I used 1 with this middle piece, right, I'd have 1 squared plus 1. This is 2. So at 1, I'm going to have 2. Let me make sure this is going to be sort of reasonable here. Yeah. So I'm going to have, at 1, I'm going to have 2. So let me do this. And again, to be clear, it's going to be an open circle. And let's do 1, so negative 2, 2. And actually, while I'm at it, negative 2 and 2. Now, last but not least, I need to know where the vertex is, because I don't know if this thing is like way down here, or if it's like through there, or if it's over there, or over here, or what, right? So to find the vertex here, I can do a lot of options. I can do, for example, vertex form, which is completing the square, right? So if I did, say, completing the square, I would do x squared plus x. So half of this, and then square, add and subtract. So this would be plus 1/4. Half of 1 is 1/2. 1/2 squared, 1/4, minus 1/4. So this would get me x plus 1/2 squared minus 1/4. So that tells me that I'm going to go to the left 1/2, down 1/4. So 1/2, 1/4, that's going to be, so if I cut that in pieces, it would be something like here, right? So this is going to be negative 1/2, comma, negative 1/4. And so my parabola is going to sort of dip down to its vertex, the lowest piece, and then come up. So it's going to go up like this, which, again, it's not a fantastic drawing, but, you know, not an art class. Okay? So that was this piece. This is the x squared plus x segment. Next one I'm going to do is 3 to the x minus 2, which, again, this is an exponential, right? So it's going to be like the Superman function, up, up, and away. But it's starting at 1, but not including 1. So I'm going to do the same cheating trick. I can't say h of negative 1 equals this because, or sorry, h of 1 equals this because 1's not even in the domain at all. So I have 3 to the 1 minus 2. That's 3 to the 1 is 3 minus 2 is 1. So keep in mind that here, right, when I did this thing at 1, I did not say this was h of 1. I have nowhere written that this is h of 1. These are two different calculations where I had this piece and I had basically scratch work, right, for these segments. And now I have more scratch work where I can't claim that this is h of 1 because it's not, right? But this does tell me that I have the point at 1, comma 1. So I have this piece. And then this thing goes up and away. And in fact, if I want to get another piece, I could plug in 2, but I'm pretty sure that's going to be like way off my graph already. So that would be, so this is at x equals 1. So now I'm going to do at x equals 2 just to get sort of an idea of roughly where it would be. So that's going to be 3 squared minus 2. That's 9 minus 2 is 7. So even at 2, it's like way off my grid here. So it's like, yeah, right? And it's strict, you know, it's the interval here goes on for infinity, right? So I can use an arrow to say it goes up and away, right? I don't have to, with the, if you go back in the video and check on A, I had it stop at -3 because that was a stopping point. Whereas here, 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 and soon here, all of these things are and so on, and so I have arrows for those, okay? Now, the last one is algebraically tricky, but the piecewise function will still sort of continue. Now, I can do this by simplifying this, or I could just plug it in and evaluate. The problem with plugging in and evaluating is it's unclear what this function looks like, because here I have a root of a polynomial, and we haven't really talked a lot about that kind of function. So you could do this by plugging in a few values and sort of figuring out what it starts to look like. So at the very least, we can sort of plug in the -1, which again, I'm cheating because it's strictly less than -1. So I can evaluate this at -1 to see what I get. So I'm going to get the 4th root of -1 squared plus 2 times -1 plus 1. So here, I'm going to have -1 squared is +1, +1 that's +2, but then I'm going to have -2, so this is 0. So at -1, I'm going to have a y value of 0, meaning that I have an open circle around that filled in blue dot, right? But then the question is, what's this look like going to the left? So again, I could plug in other points like -2, -3, -4, -5. Doing all that computation would be obnoxious, but you could start to do that and get a feel for it. The other thing we can do, though, is we can do this like our radicals, right? So we did a whole thing about like type 1 or type 2 radicals or whatever. We didn't really care about the name. We cared about the different sort of fundamental type of radical, things with more than one term or only one term. This is more than one term, so we can't simplify it as is, but we can try to make it only one term in terms of addition by factoring, which we can actually do here, right? So I can get that, and for example, so this, again, this is scratch work, right? I can take the 4th root of x squared plus 2x plus 1 and factor the inside as a polynomial. And doing that, I would get that this is really the 4th root of x plus 1 squared. Okay, how does that help? Well, if you remember in our exponential section, right, using a lot of different skills here, in our exponential section, we know that we can write the 4th power as a, 4th root as a 1/4 power, meaning that this is x plus 1 squared all to the 1/4, which is really x plus 1 to the 2/4, which is sort of, we'll be careful here, x plus 1 to the 1/2. We're going to say sort of because why? So I have to be careful because the thing inside is, right, being squared, which means that if I plug in sort of a large negative value, let's say I plug in -15 for x, I'm going to get -15 plus 1, -14 squared. Is that positive or negative? It's positive. And that's really important if I'm going to take a 4th root, right? But if I plugged in -15 here, I'm going to have -15 plus 1 is -14, square rooted. That's bad, right? So really what I have here is not x plus 1 square rooted, right, to the 1/2 power, but really the absolute value. Remember when we did that, when we evaluate, or we simplify out an even root, which is what we're doing here. We're simplifying the 1/4 down to 1/2. So it's the absolute value of x plus 1 to the 1/2. Now, what does that mean? Well, if I'm taking something to the left of -1, what's this going to be? I'm going to have -1 plus 1, that's 0, we did that part. But if I take an even bigger thing, I'm going to have a big negative plus 1, a bigger than 1 negative plus 1. So this inside will always be negative, so the absolute value is always going to force that to be positive, right? So in effect, my square root is just taking this thing and it's going to force this to become a positive root going left, which if you work out either using the absolute value, which is going to be the next set of videos most likely, or if we've already talked about it, you can do it that way, or you can sort of just at this point logic your way through the process saying, okay, well if I keep picking bigger and bigger values, I'm going to keep getting bigger and bigger results, right? If I did -5, that's going to be -4. Absolute value is 4 square root 2, right? And at the very least, when we talked about plugging in -2, -3, -4, -5, that's going to be way easier to calculate here than it would have been up here. So you can do it that way too. Either way, what we're going to get is that this thing is going to look like, so it's going to go through this point, but it's going to look like a square root going left, which is a little counterintuitive, instead of right, but it's because of how this absolute value is happening. And so our big piece here, this 4th root of x squared plus 2x plus 1 on this side is really looking like this. And I will stress I'm doing this because this is a sort of demonstration of a really tricky, difficult one to do. That's why I'm the one doing it, to show you the process, right? This is something that would be fair game like on an exam, but I would also rank this as one of the hardest problems on the exam. So I don't want to say that this is sort of the average thing to do. That being said, for any of you going on to calculus, this is a common thing to run into, and at that point this would be considered sort of the easy part of the problem. So at this point, because you're just learning it, I would rank this as one of the harder problems you have to do. But if you're going into calculus, these are the things that you need to be able to see and do. This stuff right here, right, translating it into a different kind of function you can do quickly, that's the skill that you really need to work on, okay? So finally, so we did A and B. This is C, where again I have, right, I used all of the endpoints and transition points, right? I have arrows because they are going to infinity, and I could write that, but I don't need to. I did -1 and 1 because those are transition points, but I also did, open circle where it's strictly, closed circle where it's equal to, right? And again, just as a recap to be sure we're all on the same page here, if I'm actually plugging in a value, like what is h of -1, h being the actual piecewise function, not a piece of the piecewise function. If I'm plugging in, then I have to find out what that thing equals, right? So that means I have to figure out where that is in the domains. When I plugged in -1, -1 is in this domain, right? It's between -1 and 1, including -1 is here. So that's the only row I use. I don't care about the other rows. And again, in case you're curious, or by way of sort of showing what this means, if I asked you to calculate, say, h of 1, you do the same thing. You say, okay, is 1 less than -1? No. Is 1 greater than or equal to -1, but strictly less than 1? No. Is 1 strictly greater than 1? No. I have no other things to check. So this thing is not defined. Or another thing we write in math very commonly as sort of a shortcut, DNE for does not exist. Strictly speaking, it's better to say not defined than does not exist here, because does not exist has sort of a special meaning when you do limits in calculus. But if you don't worry, like at this point, we don't need to worry about that. You can write either of these and that would be fine, okay? All right, so that is 3 examples of doing piecewise functions, calculating them, so doing like h of 1 or h of -1 or the other ones we did, as well as how to graph them, right? And each graph, again, to be clear, should end up looking exactly like geometrically what we said they were, which is 3 different pieces glued together. So this is 3 to the x minus 2, right? And it's really nice and easy to see with color coding, and for what it's worth, if you're doing an exam, you're doing a free response question or whatever, you can sort of let the TAs know at the front so they know you're going to do this, because usually we only let you have a pencil and pen. But you are perfectly welcome to bring in like colored pencils and do that. And I've had students do that, and it works out really well. So you can sort of mimic this exact process that way as well. Okay? And that is it. We are done.